Good morning, second class, and welcome to Machine Design. So, welcome back. It's going to be a fun year, lots to do, and you're kind of well into the throes of this virtual learning now, so hopefully that will make things a little bit easier. So, Machine Design, you've all been waiting for this course with bated breath, I know. This is for mechanical engineers, the kind of de facto mechanical engineering class. So we're going to literally learn the nuts and bolts of this discipline. What are we talking about? We're talking about the design of machine elements. So these are all things that kind of go into your machine, whatever that machine may be: an engine, a roller coaster, a car, an aircraft, a rocket, a Bic pen, you name it. Mechanical engineering is kind of there. So these machine elements, some are more popular than others. We're going to look at the main ones. So we're talking bearings, gears, nuts, bolts, springs, that kind of thing, and how these things all fit together. And this quote I like to start the course with because I think it kind of sums it up. This is from an engineer called John Err. I'm not quite sure who he is, but he's attributed to the quote. Engineers use materials they do not properly understand to form them into shapes whose basically geometry they cannot properly analyze, to resist forces they cannot properly assess in such a way that the public at large has no reason to suspect the extent of their ignorance. So it's a little bit kind of paranoid, a little bit worrying perhaps. Next time you're flying at 37,000 feet, you can think about that. But it's kind of true. We have linearized material properties, we linearize stress analysis, and we take that ability to analyze materials and forces and stresses, and we really kind of push it to the limit. But it's important to remember that these are always just models, and if we design something and we've done all the analysis, but it's a critical component and people's lives perhaps depend on the success of that component, then it's always worth building it and testing it, because at the end of the day, all the analysis we do is really kind of based on models, and we can get very, very good at that, but always bear in mind that you really can't beat doing some experimental testing and prototype testing, kind of thing that you're going to do in your capstone course next year. So the syllabus is online. You obviously can't read this, it's very small, but it's just the front page. The syllabus is on Microsoft OneNote, which you can get through your Teams app. So you should all, you're obviously logged on today or in the lecture to see the Teams video, the video conferencing. Well, in Microsoft Teams, there's a link to the OneNote tab. You can click on that. Hopefully you should all see that you have your own OneNote page and document tab. And this is really important because this is where we're going to do all our work this year. So all your homework assignments, your lab reports and the like, we're going to get you to submit them into those tabs in OneNote. So you can write them up in Microsoft Word or Excel or whatever we have to do, or SolidWorks. And then you can basically print them directly into OneNote. So there's no paper actually required. And then we as instructors can go through those folders and grade them directly, so there's no paper transfer. Very efficient, very sustainable. So this is kind of probably the way of the future, not just a consequence of this pandemic, but they probably pushed us to be more efficient in how we deal with this grading and basically the paper mill that is the academy. So the course, again, I'm just putting this here for my benefit, not so much yours, but this is online. If you go to your the team Microsoft OneNote page, the notebook, the class notebook, you'll see that in the content section the syllabus is shown, and you can click on that. There's a file link to the actual Microsoft Word file, and then the actual syllabus itself is printed out in OneNote, so you don't have to open the Microsoft, you can actually examine it in OneNote. There's a lot of information here. Basically goes through what the course is about: design of machine elements, like I talked about a minute ago, material strength, manufacturing, safety, stress concentration, fatigue, corrosion, etc., etc. So a lot of this stuff you have kind of covered a big chunk of this course already, starting way back at statics, dynamics, material science, thermo. Those courses will come into this course. What we're doing now is pulling all of that together and we're building on it. So this is a course that builds on that foundation. and so you will have to make sure that you refresh your knowledge and be prepared to dig that up from the dust and use it in this course. It's 4 credits, so it's a big class. We meet for lectures, obviously Tuesday, Thursdays, 8 till 9:15. The way this is going to work is I'm going to post videos each week, and the videos are effectively going to be the lecture, and then these class sessions are going to be effectively tutorial sessions where we'll all meet, so I can actually see that you're all here and with us. And you should ideally look at the lecture before that tutorial session, and any questions you have about the lecture you can bring up in that tutorial session. And once we get into this routine, I don't envision those tutorial sessions being very long. Basically, the 1 hour lecture, that is your credit hour, should be watching that video. And the beauty of the video is you can kind of watch it at your leisure. You can stop it, pause it, take notes, treat it like a lecture, but one where you can actually pace yourself to the lecture. So that's how the class is going to work on Tuesdays and Thursdays. The lab is obviously going to be virtual for the first couple of weeks, and we will see how that progresses. I do fully expect that we will have meetings, be they socially distanced or whatever the terminology is, as the semester goes on, because we'll need to have practical labs. But for the first 3 weeks, we'll do those virtually. We will be available. I'm on Thursday morning. Commander Cart is Thursday afternoon, and Mr. Camion will be Friday morning. So during those lab periods, one of us should be available on Microsoft Teams if you have questions about the lab. Usually it'll be the one of us that's assigned to that lab period, so I'll be around Thursday morning online, ready to, you can just kind of interact with me during your lab period if you have questions. So that's how the labs are going to work. Again, there's lab reports. They're going to be submitted, and we'll talk more about that in the lab. Prerequisite for the course is mechanisms. There are 3 instructors assigned to this course. It's a big class. There's almost 30 of you. It's myself, Professor Foley. I'm in room 125 when I'm at the academy, but we are online at the moment, so we're on Microsoft Teams. Commander Cart and Mr. Camion. And you'll notice that we're all PEs. That means we're all professional engineers. And we've done this job outside of academia in one form or another. So course objectives, we want to get you familiar and comfortable with speccing these machine elements that go into the bigger machine in such a way that they don't fail and they perform the function for which they are intended. Applying previous subjects seamlessly, statics, strength of materials, dynamics, that kind of stuff to design situations. Demonstrating logical application of that theory to those elements. Understanding strength of machine elements and demonstrating the proper use of safety factors, deflection in machines, using CAD, SolidWorks and spreadsheets to do stress analysis and optimization, PowerPoint to communicate, and reports. Obviously quality technical reports is first and foremost. That is your product as a professional engineer, and that's what you're going to be doing in this course. You've already had some experience at that in mechanisms and even in IMED, and Capstone is going to be the same. The textbook for this course is Shigley's Mechanical Engineering Design textbook. Nisbet and Budness are also now really the authors. Shigley's been dead for a while. Hardcover edition, please. No paperbacks. They just won't last. The good news is I think we're on edition 11, which is a paperback, so that's probably not going to be any use. But we really don't mind if you buy the 8th, 9th or 10th version. So price obviously goes down with those editions. We're not slaves to the book, so any of those editions, if you want to save some money compared to the new one, that's fine. Make the investment in the hardback though, because that will see you through your engineering career. It's a very useful textbook, and one of the kind of must-haves on your shelf. Even if it's a very small shelf, it's probably one of the ones you should have as a mechanical engineer. You will be required to have SolidWorks installed on your machine if you haven't already done that, which you should have for mechanisms, but we do have licenses available. You can talk to IT if you're struggling with that, but make sure you have SolidWorks available. That will become more and more important as the semester goes on. Okay, so I'm not going to leave that on. There is, if you look at the syllabus, there's more details on all of this. There is a schedule. Again, you probably can't read this at the moment, but interestingly, this year we have these military days, which are kind of make us lose a week 8. and then spring break where we lose another week, effectively at week 11. So there is a little bit of disruption in the middle of the semester, but we'll make our way through it. A quick roadmap that kind of breaks down that you can actually see a little bit more. The way this course is going to work is the first 6 or so weeks, 6-7 weeks, is basically a review, kind of like on steroids, going through your statics and material science, redoing some stress analysis, strength of materials, and then pushing that to some variable stresses. There'll be some thermo in there that we have to use to do some analysis on an engine, and then your report writing skills. So there's a combination of all the courses you've done already, but most of this stuff you will have seen in one form or another, maybe not used it as intensely as we're going to, but you will have seen this material, so it shouldn't be uniquely new. Once we get to around the military days, that week break and spring break, then you'll see that the material becomes new. We start going from the basic stress analysis and material selection into how that works for these particular components that we talked about, these machine elements. So shafts, couplings, threaded fasteners, how you do welding, bearings, gears, springs, clutches, brakes, etc. So this becomes more component oriented. We'll talk about the labs more in the lab period, but the labs will run obviously concurrently, and you will find that you'll have homework assignments from the lectures and lab reports, and sometimes the two of them will align and you'll have both due in a week, so it seems like a pretty big workload, and it is to begin with in the semester. The back end of the semester, the good news is that kind of tapers off. But put the effort in up front and it will pay dividends as we go through. The first couple of weeks we have some basic exercises that link up with what we're doing in the class, and then the back half of the semester we kind of go all medical school on you. We provide you with an engine, a real engine, a 5 horsepower Chinese knockoff, and that engine it's a working engine. You will take it apart and then we will reverse engineer that engine. So this is like the medical students get their cadaver at medical school that they then take apart and work on and learn the human body. You will get an engine, take it apart, learn the why things are the way they are. And then the really cool thing as engineers is that unlike the medical students, we can put this thing back together and bring it back to life at the end of the semester. So unless you're Frankenstein as a medical student, you don't get to do that, but we as engineers will get to do that. And so you will fully understand how that thing's designed, worked, and put together. So it's kind of a fun way of doing it, and it brings these components to life. Okay, thing that's close to your heart, grading. Okay, so the way the grading works is there are 2 one-hour exams in this course. So these 1-hour exams are pretty time intensive, and they are designed to stretch you. They are not walkovers. You will have to work hard and revise, and we do use these as learning exercises. So they are time pressured and quite challenging. So, but do not fear. You can then make up if you have any shortcomings there with 40% of the course available in your lab work and reports, and this portfolio that you build up. By the end of the semester, you will have electronically a portfolio of reports. That's actually quite something to be proud of, I should think. And then there's the final exam, 30%. This isn't time pressured. This is not set to try and trip you up. It's not really a learning exercise. It's for us to see how much of the stuff you've taken in and learned. And so people can usually recover quite a bit of their grade if they've had trouble with these. And overall, everybody kind of gets through. But we do want you to study and work for these 2-hour exams. You'll keep a binder, an electronic binder with all the coursework and assignments. You want to keep an index, and you can do that on OneNote, an index of all your reports. Just have a page at the front of your assignments where you can index them all. Cover sheets on all of your reports, and you're going to use the correct drawing formats as well, which we'll talk about in the lab. Okay, so that's so much for the admin. Things might change and will be a little fluid as we go, depending on how things pan out in the pandemic. But the first thing we're going to start with, so this is kind of the material proper, is we're going to do way back when, 2 years ago, when you did statics, a quick review of some statics. Make sure that's all fresh in your mind. So, statics, what do we remember? Well, because it's static and it's not moving, basically the sum of the forces is 0 and the sum of the external moments is also 0. And that's about on all three axes. We live in a three-dimensional world, so all three axes, these should be 0. Quite frequently we'll have problems where these collapse to one-dimensional, two-dimensional. Two-dimensional is more common, and we can just ignore the third dimension because there's no forces, or we're told there's no forces in that third dimension or no moments. But do remember we do live in a three-dimensional world, so we sometimes simplify, but always be aware that there is the potential for something else to be going on. An inertial frame of reference, we use the Earth, and obviously the Earth is spinning around itself and then spinning around the Sun, and the Sun's spinning around something else, so you can get carried away, but for the inertial frame of reference being the Earth, that works. 6 equations here. We need to isolate the system on which the forces and moments we consider act, and for that we use the very important free body diagram. So this is a pet peeve of all academics, engineering professors, is for some reason next year in your senior projects you'll come out and you'll do presentations where you'll show the body or the subject that you're working on and the forces acting on it, and it will not be in equilibrium, and you will not show accelerations, you won't show all the forces, and so that really becomes a kind of a worthless diagram. So please do not forget this, okay? If you're going to draw a body with forces on it, show all the forces and make it clear that it's a statics problem, they're equal to 0, or show the resulting accelerations. Okay, otherwise you're only telling 2 chapters of the 10-chapter story. You need to show all the forces on a free body diagram and make it clear that what you're showing is a free body diagram. So free body diagrams, basically we decide the body which we're going to analyze, and then we kind of look at that in isolation. Identify all the bodies that touch the system or exert significant gravitational or magnetic forces, and then identify forces and couples from part 2, all that external stuff, and show these on your sketch. So some of the forces for a statics problem, moments equal 0. Dynamics is not that much more difficult, and a little trick I use is with the dynamics problem, if I treat the acceleration as a force, bring it over to the other side, I've got a statics problem. But we're talking statics at the moment. So the sum of all this stuff is 0. Draw the free body, show all this stuff on it, and then we can start to find relations between these forces and moments. So let's do a little example. So what we've got here is it's a three-dimensional problem in reality. We've got a box, a cube, and this kind of wedge cheese thing that's pushing its way under. And because there's not a lot of interesting stuff happening in that third dimension, there are no forces acting into the paper and out of the paper, and we can reduce this to a two-dimensional problem. So we have a 200-pound cube resting against the wall and supported on its bottom left corner here by this wedge. The wedge is pushing into the cube and basically supporting it at the moment. There's a static coefficient of friction for all of the surfaces of 0.6. This thing is static, it's not moving, so we want to solve this problem by identifying 2 free bodies. Okay, so we're going to look at this cube and this wedge as 2 separate free bodies. We're going to analyze those, do the sum of the moments and the forces, and then we can actually basically solve for what force P is required to keep this system in static equilibrium. So there's no weight on the wedge, this is just a shell, and then this is the actual cube with the weight in it. Notice there's no dimensions here, no dimensions are actually required. Friction is just F equals mu n, there's no mention of area in that, it's just to do with forces. So let's start, we'll no particular order, we'll just start the way I've done here is with the wedge. You could start with the cube, it won't matter. And we're going to draw the free body, so we draw our wedge, and then we're going to identify and label all the forces. So we have the force P, which is shown here, and then we know that there's a contact surface here, so there's some friction. The way it's shown here is P is pushing in. Okay, the assumption is that P is going to be positive because the weight wants to drop and it's pushing this out. Again, if we make the assumption wrong, then P should come out to be negative. The math will sort that out for us, so it's not the end of the world if we've got that the wrong way around. It's just important to show the force directions on your sketch and then to stick with those the way you introduce them into the problem. So plus from left to right, and down. Make sure that you are consistent with your directions and your signs. But for all of my subjects, I always state, draw the sketch, show the forces, and then use this actually defines what the variables are. So W here I know is going to be the weight, P is the restraining force. I don't have to write that down somewhere, it's kind of defined in the sketch. And then the direction of these forces is also shown. And that direction then transfers into my equations, whether or not it's plus or minus. Okay, so let the sketch, very, very important, it defines what the symbols are and the forces are, and it defines their orientation. Okay, so here's the wedge. We've got P coming in. If P was pushing it this way, I'm assuming there's going to be a friction force to stop it sliding to the right. So I'm going to show my F2 here. There is some force acting down on it due to the box on top, and so that will manifest itself as a reaction pushing up to stop the wedge sinking into the ground. So there's a vertical force, horizontal force, and they're going to be related by the coefficient of friction at the point of slipping. We're trying to find P, the smallest force that would be required to hold this thing in equilibrium. At the point of contact, there's a contact at this point, there's going to be a reaction perpendicular to the surface, R, we'll call that R1. And again, because we're pushing the wedge in, there's going to be a friction force pushing back, trying to stop the wedge from moving from left to right, and I'm going to call that there F1. So I've got an F1, R1, F2, N2, and that is all of the forces. There is no weight in this wedge, so I don't have to show that. So now, once I've got that free body diagram, and that's 80% of the problem, is getting a good sketch. Okay, so now I resolve horizontally. So there's a lot going on here, do not fret. So by resolving horizontally, let's bring the sketch back here so we can see what we're doing. Okay. So I've got my P from left to right is going to equal my F2 from right to left. Again, the signs are defining the direction. I've got this F1 here, and the cosine of this angle theta, which is 30 degrees. I'm just going to use the theta for now, just to save on the numbers. So it's going to be F1 cosine theta acting backwards, plus R1. R1, make sure clear, R1 is this force, not the vertical one. R1 times the sine of theta is also acting back against the P. So that's my horizontal. I do know that F equals mu n. Friction equals the friction coefficient times the normal force by definition. It's proportional constant proportionality there. So now I can actually eliminate the friction variables and just work with the reactions. So F2 is going to become mu N2, F1 is going to become mu R1. So this equation collapses to this equation 1. So this is my equation 1 from resolving horizontally. What's next? Well, you guessed it, we're going to resolve vertically. So coming back here, resolving, going vertical now, I'm going to have my N2 acting up, plus I've got a component of this F1. F1 times the sine of theta, that's also acting up, that component there. And that's equal to the forces acting down is R1 times cos theta. So forces acting up, forces acting down, and again we can now eliminate the friction with the F equals mu n relationship, and I'm left with N2, I'll put it on this side, equals R1 cos theta minus mu R1 sine theta. I'm just collecting the like terms, the R's and the thetas on this side. So that's my equation 2. So what am I going to do next? Well, I've got two equations, I've got a bunch of unknowns here, more unknowns than equations, so I'm not going to be able to solve it at this point, but I can simplify these two equations. So putting 2 into 1, so I'm going to put the N2 into here to eliminate N2. P now equals mu times N2, so mu times R1 cos theta minus mu R1 sine theta. Let's keep R1 in there. Plus mu R1 cos theta plus R1 sine theta. So this is my 2 into 1. Now I'm just going to clean this up a bit by factoring out the R1. Bring the R1 out here. I've got a R1 cos theta there and R1 cos theta there. So I've got two of those, so I can bring that 2 in there, 2 mu cos theta. I've got a mu times a mu r1 sine theta and a mu r1. I've already got that, so I've just got the 1, so that becomes mu times r1 squared, so the r1's out, so the mu squared sine theta plus the sine theta. So I've basically just factored out the r1 here. So that I'm going to call my equation A. So I still have one equation, 2 unknowns here. I've still got P and R1 as unknowns. I know theta and I know mu, so I know everything else, but I don't know P and R1. I've got an equation with 2 unknowns. So the way we're going to tackle that, go back to our original sketch, we're now going to look at the second body. So you know that's going to eliminate some of those variables. So we take the cube, the block, should I say? Okay, so let me draw. Now I'm getting my notes mixed up. Right, so we're onto the block. Okay, so I draw my block. Looking at the block, and again going back to the original sketch, we've got the weight of the block is shown. It's up against the wall. If we're pushing the wedge in, the inclination is that we think this would go up, so the friction is going to be acting down, F3. It's been pushed against the wall, so there's a reaction there, N3. And then this point of contact, Newton's second law, equal and opposite forces. We had an R1 acting onto the wedge, so we've got an R1 in the opposite direction acting up onto the block. And then we had friction acting up the wedge, so friction here is acting down in the opposite direction. And then I've just brought in the theta angle. So what we have here is, if you look at this next to each other, I can lay that up. Here's the R1 acting down, the F1 acting up there. We just flip the direction of those two around and put them acting on the other body. So equal and opposite. Okay. So now with my box, we're going to do the same exercise as before. Okay, so we are going to resolve vertically. So we've got a R1 cos theta acting up minus an F1 sine theta acting down. We've got the W here acting down, so it's minus a W. And then we have the F3 acting down, so minus F3. All of that, because it's in static equilibrium, equals 0. So let's tidy this up a bit and get rid of the friction forces by using the F equals mu n relationship. R1 cos theta minus R1 mu sine theta minus W minus mu n3. So that's my equation 3. And then I'm going to resolve horizontally. So again, looking at our sketch, horizontally I'm going to have R1 sine theta acting to the right, plus the F1 cos theta acting to the right is equal to the only other force there is the N3 acting from the right to left. So again, with this one, we can eliminate the friction force with mu. So we can get R1 sine theta plus mu R1 cos theta, and then all of that equals the N3. And now I'm going to substitute for N3 back up into this equation. So there's a lot of algebra here, but it's not particularly difficult. Just going to make sure you don't make mistakes. So with that substitution, we end up with this expression. Okay, we're going to clean this up, collect like terms together, and our W in this case equals, factor out the R1. We've got a single cos theta there. We've got a mu squared sine theta there and a mu squared sine theta there, so it's minus 2 mu sine theta. And then we've also got a mu times a mu there, so mu squared cos theta, which goes in there. So this is our reduced equation for the block from resolving vertically and horizontally. And I can rewrite this as R1, which is one of the unknowns in our equation A. Remember equation A here, 2 unknowns, R1 was the unknown. So R1 equals W over this, so we know everything in here, so we can actually find R1, because we know W mu and we know theta, so we've got R1, and then we can substitute that back, this B, into equation A, and now we have P equals, all of this is known, and so we can solve for this. 200 mu is 0.6, theta is 30 degrees. Plug all the numbers in, and we end up solving for P coming out to be 235.5 pounds. So the rest of it's just a formality. So we used 4 equations. There's an awful lot of algebra there. So it looks like a relatively simple problem, and it is. It just requires a lot of algebraic manipulation. So we're having to push this direction to maintain this weight, stop the whole thing from falling down. So what do you take away from this? Big sketch. This sketch is too small. I always want a sketch to be a minimum of half a page. Draw a sketch of the complete assembly or wherever it is, and then your free body diagrams, extract them, draw all the forces. In this case, there were just forces. There was no moments for this example. Sometimes that's not enough. We'll have to take moments. We didn't take any moments in this one. You don't always have to use everything. If you can solve it without, that's fine. And you can solve it in numerous different ways and end up with the same answer. You don't have to start with the wedge. You can start with the block. There's a number of ways of doing this. Big sketches, and then work methodically. I wouldn't put numbers in early. Stick with variables while you do the algebra. And the beauty of that is that I can now, once I've solved this, if you go right to the end here, these equations for R and P, I could program them into Excel, and then I could change the angles theta, I could change the weight, and solve for different reactions and different P's. Where if I'd have actually, used the sine of 30 degrees all the way through in the numbers, I wouldn't have this useful form here, this algebraic form with the variables. Because what you'll find is, many times we're going to do this, we're going to solve, and then we're going to want to optimize. So we want to go back and we want to change some variables and see how this works. And before you can do that on a computer, you need to solve it algebraically by hand, and then you program it in, verify that first calculation you did by hand with the computer, and now you have confidence in the computer solution, and then you can do the optimization on the computer. But you must do the hand calculations first. Okay, so that's one example. I'm just going to do one more today, and this one I'm going to do because we have moments in it. The first one was just resolving vertically and horizontally. So what we've got here is some kind of table arrangement. So there's a cantilevered beam effectively that comes away from a wall, and then there's this pinned joint here with a roller on the end. And this solid bar here is also pinned with another bar here that goes down to a pin joint there. So I imagine somehow you could probably pull the pin out of here and then let the whole thing collapse. So kind of thing I'd probably find on a boat. But once this is locked here, this pin joint is locked in place, holds this roller, supports the table. We have 890 pounds, so it's a pretty substantial load on the end. We've got these distances, 5D, 3D is the distance out to the roller here. 4D is the distance up. D is 30 inches, but again, we're going to leave it as the variable D because that's the more useful way to solve it. So this is the sketch, and what they want is the force that this bar FD places on the bar CE, or CDE is one continuous bar here. So this is pushing up on this CE, CDE bar. What's the force? So what they want is the force that this thing's in compression. What's the force in that bar? So again, start off by drawing a big sketch. So I've just redrawn it, but a little bit bigger here. I have 5. I should put the D's in there because it's still, these are D's. That's 3D, so it's not 3 inches. 890 pounds, cantilevered beam. So this is the whole structure. Some angles of interest here, theta, not given, but I can work those out from the geometry. So now I'm going to do the free body diagram. I'm going to start by looking at the cantilevered beam. So this thing here that's pinned, if this structure was taken away, this could spin around. So just by looking at this first, I'm going to draw it in isolation. So there is A and B. This roller is going to be able to exert no friction because it's a roller, so it can only provide a vertical force up. So that's what my force R is here. And now I can look at this, and you can resolve vertically, horizontally, and you can find the reactions here by drawing more forces on. So I really should draw a force on there to be a complete free body diagram. So there's an R acting up, which is balanced by, this force acting down, and then there's going to be a reaction also at this point here. There is no horizontal forces, so I don't have to find those, but we should draw all the forces on. Turns out I don't need to solve for this force here. I could, but I don't need to. So what I'm going to do is I'm going to take moments about the pin joint here. And again, if you do take forces and solve them, it's not the end of the world. It just means you've spent a little bit longer on the solution, but you'll get there in the end. So we take moments about this pin joint here. I've got 5 is the distance, 5d if you will. Again, I can write it here. 5d times that force F, and I know what F is, but I'm just going to call it F to keep it all algebraic, is going to be equal to, that's clockwise moments, is going to be equal to the anti-clockwise moments, which is going to be your 3d times your R. The d's cancel, and that's why I didn't put them there. So my R force is going to be equal to 5/3 of F. So I already know that if F is 890, I've already got R is 5/3 of 890, which is 1,483 pounds. Boom, pretty straightforward so far. So with that first section kind of analysed, now I'm going to go on and look at the next thing. It's like the knee bone's connected to the thigh bone. You're kind of working your way around the circuit. So this is another basically cantilevered beam, if you will, that's supported at its midsection by this bar. So I'm going to draw this as my free body. Okay, so this is my CDE. And I've got the force R, we just calculated that, and I'm trying to find the force that this DF puts on it, and that's, again, we're told it's perpendicular, it's given as perpendicular. So I can now, again, just take moments about C. So from C, I am going to have this force here is acting at a distance 3 from that point, perpendicular, so it's 3D times R, clockwise moments, if you will, they're clockwise, is going to equal the only anti-clockwise moments about here is going to be this F force, FDF, times this distance, 2.5, or 5/2 D. D's going to cancel. So my FDF equals 6/5 times R. We've already solved for R, so my FDF equals 1,780 pounds. And that's the force, the compressive force that's in that bar that's holding that cantilevered beam, if you will, in place. So again, much simpler problem than the last one. Doesn't look like it's going to be simpler to begin with, but all we did is took moments about this point and then this point, and we've solved for that compressive force there. So again, no resolving vertically or horizontally required there. So those are 2 examples that are kind of extreme. Usually we have to do a bit of both, take moments and resolve vertically and horizontally, and kind of mix them up to solve. And there's just 2 examples where we just did one or the other, but normally you'll have to do both. And the next lecture we'll do 1 or 2 more examples on that. So hopefully that's given you a flavour. It's getting you back thinking about big sketches. Draw all the forces and dimensions that are relevant, any angles, all the information you got, put it on a nice big sketch to begin with, and then redraw the subcomponents. Students quite often will do the one sketch and then do the analysis on that one sketch. I can't stress enough how important it is to not do that. Draw the sketch for informational purposes, and then for the analysis, break it down into the free bodies and look at the forces on the body on its own, and then solve and work your way through. Try and keep it all algebraic as long as you can, so that you can later come back and optimize it. Okay, so that's it for today, for the kind of little statics review. And I will see you in lab or in class next. Take care.